So we were seeing about double tuned amplifiers, and I told the derivation is big, and we are halfway through the derivation. So just to give introduction about double tuned amplifiers, so you will be having a couple of tuned circuit in the collector. So you will be having a pair of inductors and a pair of capacitors. So when you have two inductors, generally we replace it with a transformer. So on both sides of transformer, you will have two capacitors. So in the diagram, you can see. So in a transformer, on the primary side, you will have an LC combination. The secondary side, you have an LC combination. So this is going to act like a tuned circuit. And the most important thing is this LC and this LC are tuned to the same frequency. And you can have multiple stages of double tuned amplifier for having better selectivity of your application. So we have directly drawn the output side equivalent circuit, and we have converted that into a simplified circuit for applying KVL. So this is the final circuit we got, one loop on the primary side, one loop on the secondary side. So we applied Kirchhoff's voltage law, we got two equations, and we found out the value of Z in, and we found out what is the condition for maximum power transfer in Z in. So at resonance only the maximum power transfer will take place. At resonance, the Z in value was found to be this one. With this expression, this circuit is redrawn. So, and we have found out what is the critical coupling coefficient Kc. And Kc depends on the quality factor of the input side and the quality factor of the output side. That is the value of critical coefficient of coupling. So this we have found a specific case where everything happens at resonance and at a critical value of coupling Kc. Now we are going to move to a general case where the coupling coefficients are not critical. So in a general case, you see K is not equal to Kc, which means that K is a fraction of Kc. And M is a fraction of MC. See, K is coupling coefficient and M is mutual inductance. Okay. So in now other cases, other than your resonant condition, your value of coupling coefficient will be some fraction of the critical coupling coefficient be Kc, and your mutual inductance will be some fraction of the coupling critical mutual inductance Mc. So that will be both are a same fraction B because K and M are related, correct? You know K is equal to M by root of L1 into L2. So since K and M are related, if a K is going to vary by a factor B, M will also vary by the same factor small b. Now I am writing the same equation which we have considered V1 equal to I1 Z11 plus Z12 I2, 0 equal to Z21 I1 plus Z22 I2. You know Z12 because the mutual inductance is going to be same. Z12 will be equal to Z21, and as usual what you did, you find I2 from this equation. From the second equation rearrange, you get I2 Z22 I2 equal to minus Z21 I1, and you substitute the expression for I2, and you find substitute that in the equation to get what is Z11, Z22, Z12 and 21. See, these four things we know in the circuit. The Z11 is going to be in the input side what all components we have. Z22 in the output side what all components we have. Z12 and Z21 both are going to be j omega m. And you know in during resonance these two reactances will cancel each other because they are tuned to the same frequency. So omega naught L1 will be equal to 1 by omega naught C, and omega naught L2 equal to 1 by omega naught C2 dash. So at resonance, the reactances will cancel. The circuit will be working like a pure resistance. So at resonance, you see this term will go Z11 will be equal to R naught dash. See the next slide. Z11 equal to R naught dash. Z22 you see this reactance term will get cancelled. Z22 will be equal to Ri dash, and Z12 and 21 will not have any change. They will be equal to j omega m. Okay, so this is going to be the condition values at resonance. See, at resonance we are finding out, but at non-critical values of K and M. When you put M is equal to MC at resonance, you know at resonance M will be equal to MC. So Z12 and Z21 will be equal to j omega naught MC. Now substitute everything in the expression for I2. See, I2 normally this is the equation. At resonance, this current will be maximum.